Welcome to Unit 4, Lesson 1. In this unit, we'll be using the trigonometric ratios. So we will be reviewing what we have to know, especially sine, cosine, and tangent. So in real life, very often we deal with diagonals. For example, in the picture to the left, there's a ladder. We see that the ladder is 10 meters long. We see that the bottom of the ladder is 5 meters from the bottom of the wall. We want to know how high the ladder is. Well, when that happens, what we have is a right triangle. If we know two sides, we can apply the Pythagorean theorem to help us solve problems. So for this one, let me spell Pythagorean theorem correctly. Theorem. We see that the hypotenuse is the longest side, so we know that this side is called the hypotenuse. Hypotete. Neuse is Neuse. That's the longest side. H must be shorter than the hypotenuse, so we know we're subtracting. So what we're doing is to find the height. We know the height squared has to be 10 squared, the length of the ladder, that's the diagonal, minus 5 squared. If we're going to do that, that's 100 minus 25, which is 75. So the height should be the square root of 75, because we take the square root of each side. Okay. Here's another example. Every day if I walk to Bada, to walk to school, I'm walking from Park Street. So here's just an image taken from Google Maps. If I start here, let's use orange. So I'm starting here around the Park Street station. Bada is all the way over here. So I'm trying to get from Park Street to Bada. Now, I might know how long the streets are. I can go down Tremont Street, turn right, or I can cut the diagonal right across Boston Common. If I know this side, if I know the length of Tremont Street, and I know the length of, I forgot what street this is, but if I know the length of these two streets, this is roughly a right angle. I can find the length of the diagonal. Okay. So if we know two sides, we can apply the Pythagorean theorem. The diagonal is a squared plus b squared. A and b are the lengths, the two other sides of the triangle. Okay. But in real life, sometimes we only know one side. For example, about 2,000 years ago, a little more than 2,000 years ago, about 2,500 years ago, Aristarchus tried to figure out the distance from the Earth to the Sun. What he figured out is that when we're at a half moon, it's roughly a right angle between us, the Earth, the Moon, and the Sun. So in this diagram, we see that we can figure out the angle between the Moon and the Sun. If we know this angle, we can figure out the ratio between our distance from the Earth to the Moon to the distance from the Earth to the Sun. Okay. So to solve this problem, we're going to need to use trigonometry. Here's a problem closer to Earth. So I'm pulling a box. Well, this woman in this picture is pulling a box. She's pulling the box to the right. The thing is, in real life, we're not pulling exactly to the right. She's not kneeling down. She's much taller than the box, so she's not pulling directly to the right. She is pulling with a force of 30 newtons, but she's pulling with a force that's 15 degrees up from the ground. So she's pulling mostly to the right, but 15 degrees up from the ground. So to figure out how the box is going to move, we have to figure out how much force is being exerted to the right. We want to figure out what this is. To do that, we have a right triangle like this. Because she's pulling to the right 15 degrees up at 30 newtons. The angle is 15 degrees. What we really want to know is this side. To solve this problem, we're going to have to use the trigonometric ratios. What we're really saying is, let's call this missing side x. Well, we actually know that there's a ratio. In this case, the cosine of 15 degrees is x over 30. And cosine of 15 degrees, well, this ratio, we know what the value is for every triangle. We know the ratio of this side, which we're going to call the adjacent side, to the hypotenuse whenever the angle is 15 degrees. So we can use a calculator to figure that out, and then we can figure out what x is. So we'll come back to this later. Alright. So here are the trigonometric ratios. Sine, cosine, tangent, secant, cosecant, cotangent. Given any angle, like this one, the hypotenuse is once again the longest side. Adjacent means next to. Well, the adjacent side, just like the hypotenuse side, is next to our angle. So that's why it's called adjacent. Opposite is the one side that is not next to our angle. So that's called the opposite side. Sine of our angle is always opposite over hypotenuse. Cosine is always adjacent over hypotenuse. And tangent is always opposite over adjacent. Sometimes people use the shortcut SOHCAHTOA to remember these ratios. So, SOH, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. TOA, tangent is opposite over adjacent. And really, if we know sine, cosine, tangent, we can solve all of these problems we've discussed so far. For calculus, you should also know that cosecant is 1 over sine. So cosecant is CSC. Cosecant. Secant is 1 over cosine, and then cotangent is 1 over tangent. Okay. So let's look at this triangle. We have an angle. I'm going to call this angle theta. That's a very common name we use. This is a Greek letter. We have two sides, A and B, and the hypotenuse h. Given theta, well, sine theta, sine is opposite over hypotenuse, so is A over h. Cosine theta is adjacent over hypotenuse, so cosine theta would be B over h. Notice that sine and cosine can't be larger than 1 because A has to be smaller than h, B has to be smaller than h. And then tangent theta, tangent is opposite over adjacent, that's A over B. Okay, so sine, cosine, tangent. And then cosecant is 1 over sine, so it's h over A. Secant is 1 over cosine, so it's h over B. It's just inverse of cosine. Cotangent is 1 over tangent, so in this case it's B over A. Okay. Now let's use this to solve problems. Here are some examples. Example 1, we have a triangle. The legs are 8 and 15. The hypotenuse is 17. We want the angle W. W is uh is next to 8 and 17 and across from 15. Okay, so here's our angle. I'm gonna call it theta. We want the tangent. Well, tangent of theta is opposite over adjacent. Uh, Adjacent, well, the hypotenuse is the long one, that's 17. Adjacent is the one that's not the hypotenuse, but next to our angle, that's 8. See, the adjacent is 8. Opposite is far away, which is 15. So tangent theta equals 15 over 8. In other words, theta is the inverse tangent of 15 over 8. Okay, which we can use a calculator to solve. If you don't have a calculator, you can always use Google. Let's go to Google. The inverse tangent is also, we call it arctangent, and it's 15 over 8 in degrees. If we do that, we get, Google tells us it's about 62 degrees. So this angle is about approximately 62 degrees. Okay. Next example. Okay. Example 2, find the cosine of angle C. Our triangle, the legs are 5 and 12, the hypotenuse is 13. C is next to 5 and 13, and 12 is opposite. Okay, so we want cosine. Let's call it theta again. Cosine of theta. Cosine is adjacent over hypotenuse. The adjacent one is 5. Hypotenuse is 13. That means theta is inverse cosine of 5 over 13. Again, we can go to Google. Arc cosine of 5 over 13 in degrees. Google gives us about 67 degrees. So that's it. So theta is about 67 degrees. Okay. All right. Example 3. This time we have really the more common sort of problem we see in real life. We have a triangle here, right triangle again. The hypotenuse is 4. We know that angle T, which is 60 degrees, and angle T is in between our adjacent and hypotenuse. We want to find TU. So we're using this angle, 60 degrees. Given this angle, TU would be the adjacent, and UV would be the opposite. We have the adjacent here, and we have the hypotenuse. Well, we want to know the adjacent, and we have the hypotenuse. This means that we can use cosine. We can also use secant, but either way works. So cosine theta is going to be adjacent over hypotenuse. Our angle is 60 degrees. Cosine of 60. Adjacent we don't know. The hypotenuse is 4. Cosine of 60 degrees is 0.5. If you're not sure, you can use a calculator. 0.5 is our adjacent over 4. So our line segment has length 8. Because we multiply both sides by 4. I'm sorry, I made a mistake here. The adjacent has to be 2. Because we multiply both sides by 4. 2. And that makes sense. This side is shorter than the hypotenuse. Okay. Next, example 4. One last example. We have a triangle, EFG. The hypotenuse is EF. We know that given this angle, that's 30 degrees. We know that the adjacent is 4, and we want to find the opposite. Either tangent or cotangent uses adjacent opposite. We can use either tangent or cotangent. I'll use tangent. So tangent of 30 degrees is going to be opposite over adjacent which is going to be, we don't know the opposite, we know the adjacent is 4. Tangent of 30 is 1 over square root of 3 plus over 4. Multiply both sides by 4. So is 4 over square root of 3. If we want to simplify, we can do 4. If we want to rationalize the denominator, it will be equal to 4 square root of 3 over 3. So that's our answer. Okay. Now, if we go back to our box problem involving pulling the box, we know one side. We know that we can do this triangle. We know the angle is 15 degrees. We know that this is 30. What we really want to know is this force. How much are we pulling to the right? That tells us how the box is going to move. Well, given this angle, this is adjacent. So we can use cosine of 15 degrees as our force, the adjacent, over 30. So our force, multiply both sides by 30, force is going to be 30 cosine of 15. And we can use Google again. So 30 cosine of 15. Let's be specific. It's 15 degrees. 30 times cosine of 15 degrees is about 29, which makes sense. It's almost 30 because it's pretty close to. It's about 29. So roughly 29 of the 30 newtons is being used. I shouldn't say it that way because it's the Pythagorean theorem, so it's not that 20. It's not like this is 1. This can be bigger than. This is actually going to be bigger than 1. But we know that given this triangle, the horizontal component is about 29 newtons. In fact, as we have seen, really, given this, whatever this force is, this is always just the cosine. So that's why if this is F, the horizontal component is really F times cosine of theta. Okay. All right. That's it for the quick review of sine, cosine, and tangent.